The materials needed are 2 paper clips, a magnet, copper wire, a highlighter, 4 alligator clips, a 9-volt battery, 2 electrical wires, a Sharpie, scissors, and tape. The first step is to shape 2 paper clips as shown in the video. The second step is to take your copper wire and wind it around a small cylindrical object like a highlighter, making 12 to 15 loops. The third step is to secure the loop with the small pieces of copper wire and to leave around 2 inches of straight wire on each side of it. The fourth step is to strip the wires on both sides of the loop completely using sandpaper. The fifth step is to tape the paper clips onto a piece of cardboard, creating a rig on which the rotor can spin. The sixth step is to place alligator clips on the ends of 2 electrical wires and then to attach them to the bottom of the paper clips. The seventh step is to place alligator clips on the opposite ends of these 2 electrical wires and then to attach them to a 9-volt battery. The eighth step is to secure the electrical wires to the cardboard using tape. The ninth step is to thoroughly Sharpie 1/2 of one end of the copper wire and then to set up the magnet and loop on the rig as seen in the video. Now your motor is complete and ready to work.
In our setup, a bar magnet supplies a magnetic field and a 9-volt battery supplies a potential difference. The conventional current flows from the battery to one of the paper clips, through the coil of the wire, through the other paper clip, and back to the battery.
A magnet creates field lines much in the same way that charges create electric field lines. Outside of the magnetic field lines are directed from the north pole of the magnet to the south pole. When a charge enters a magnetic field, it feels a force, the magnetic force, that is perpendicular to its velocity and to the magnetic field lines, noted with the letter B. When a wire is carrying a current in a magnetic field, it also feels a force, since current is the flow of charges. The magnitude of the force depends on the amount of current flowing through the wire, the length of the wire, and the strength of the magnetic field. The magnetic force can be calculated with the following equation. F equals I times L cross B, also known as field. Force is a vector, meaning it has a magnitude and a direction. You can use the right-hand rule to determine the direction of this force and thus the direction that our motor will spin.
It can be noted that we will only look at the sections of the wire where the current is perpendicular to the field lines when the loop is vertical, in order to simplify the problem and since they feel the most force. In reality, all segments of the wire where the current is not parallel to the magnetic field will feel some force.
So this is how the right-hand rule is used. In this scenario, the magnetic field lines are pointing upwards due to the north part of the north pole of the magnet being on top. First, let's take a look at the top part of the loop, where the current flows perpendicularly to the field lines. The first thing you have to do is point your right hand in the direction of the current. Then, curl your fingers towards the direction of the magnetic field, which is upwards. Your thumb will indicate the direction of the magnetic force felt by the current at that spot. Here, the force is directed into the board. Now let's look at the bottom of the loop. Using your right hand, point your hand towards the direction of the current and curl your fingers towards the field lines, which is upwards. And the thumb will be in the direction of the magnetic force. Here, it is out of the board. This means that overall, the loop will want to rotate this way. Using the right-hand rule, we determine the direction of the force on the top and bottom of the rotor. Since the top and bottom experience opposite forces, the rotor will experience a torque, that is, a tendency to rotate. The more loops there are in the rotor, the greater the experienced torque will be. This is due to the fact that if one current loop experiences a force, by vector addition, 2 loops of the same current would experience twice the force, and so on. A rotor of n loops will therefore experience n times the torque.
However, there can be no energy conversion until there is something to oppose the conversion. This is a fundamental law of nature. That means that the electrical energy cannot be transformed into mechanical energy unless it must overcome something that is opposing it. In the case of DC motors, there's something called back EMF that allows the conversion. You may recall that electromotive force, or EMF for short, which is not actually a force at all, is a potential difference across the power supply, or in our case, a battery, when no current is being drawn. The rotor is consisted of coils. As these start turning in a magnetic field, they cut the magnetic field lines and an EMF is produced in accordance with Faraday's law of electromagnetic induction. Faraday's laws explain the relationship between electric circuits and magnetic fields. Faraday's first law states that if a conductor is rotated in a magnetic field, an EMF will be induced across it. And if it's a closed circuit, a current will flow through it, which is what happens in our own DC motor. Basically, as the motor turns, it also acts as a generator. This is what is called the back EMF. It always acts against the voltage supplied by the battery and it reduces its total current. Lenz's law states that the generated EMF will always oppose the change that created it. Motor speed is proportional to the back EMF. In fact, the applied voltage has a force current through the motor against the back EMF. The electric work done in overcoming and causing the current to flow against the back EMF is converted into mechanical energy. Therefore, energy conversion in a DC motor is only possible due to the production of back EMF. Since the voltage supplied and the resistance in the wires are usually fixed values, the value of the back EMF will determine the current drawn by the motor. If the speed of the motor is high, then back EMF is large and hence the motor will draw less current and vice versa. Because of this, the DC motor is essentially self-regulating, meaning it will draw enough current to develop the torque required. We can control the direction that the motor will spin by varying the direction that the current goes through the rotor, by switching the battery LEDs, or by simply flipping the magnet over.
So, we've explained how the motor starts moving, but quickly we run into another problem. Once the rotor has turned 180 degrees, the segments that we previously considered top and bottom have now reversed, but the current still flows in the same direction. Using the right-hand rule, we can see that the forces acting on the top and bottom of the rotor are now the opposite of what they were. This means that the rotor will never complete one full turn.
Now, let's use the right-hand rule when the loop has rotated 180 degrees. So this part of the loop used to be on the top, and this part used to be on the bottom. So let's look at this part first. Point your hand towards the direction of the current, and curl your fingers towards the field line, so upwards. The thumb is in the direction of the magnetic force, which is into the board. Now, for the top part, pointing the right hand towards the direction of the current, and curling towards the magnetic field lines, we see that the magnetic force goes out of the board. This means that the loop will want to rotate this way.
Luckily, there are several ways to circumvent this problem. The simplest is the following. Strip only the top or bottom of one of the pieces of wire that touches the paperclip support. The rotor will complete half a turn, then the circuit will be broken as a non-stripped part of the wire touches the paperclips. Since there is no current for a split second, there is no force because there are no moving charges in the wire.
Therefore, the motor will not feel that opposing torque that prevented it from spinning continuously. Instead, its inertia carries it through until the stripped part of the wire is once again in contact with the paperclips, which completes the circuit.
The rotor now experiences a torque in the same direction that it originally did, and it keeps rotating without stopping. In the case of our own motor, the edges of the wire were both completely bare. This means we have to find another way to insulate one part of the wire. To do this, we use a Sharpie marker and color the top part of one of the bare wires. When the part covered in Sharpie comes in contact with the paperclips, the current is momentarily cut, which produces the same effect as mentioned before.